what I'm going to do, I have a short application that I want to point out. It's one that we'll be doing as a problem when we get to the lecture on, to the class on Thursday. I want to highlight the key steps. What I may do, depending on how Thursday goes, is post a more detailed version of it. But this is the number one idea of why we end up using complex numbers. And it's this idea of phase shift and linear systems. And what do I mean by that? Well, what does it mean for something to be a linear system? Anyone have an idea, learned it, remember it? If I say L is some operation that is linear, and it's going to act on things A and B, what does it mean for it to be linear? Exactly, what all of you said. I can write this as L acting on A plus L acting on B. Give me an example of a linear operation. Derivative. What else? What's what? Multiplication. Right? Derivatives, multiplication, integration. Most of the things we do in physics are linear operations. Taking the sign of something is not a linear operation. But most things we do are. So what this means is, since a complex number is an x plus iy, if I have a linear system acting on z, by definition, it acts on the real and imaginary parts separately. Because the other thing about a linear system is the linear system acting on a constant times a is the same as the constant times the linear system acting on a. Those are the two pieces. This is fact number 2, and that's fact number 1. And because of this, the fundamental thing we can do is, if we have some behavior where we're starting with a cosine theta type behavior, I can then write it as r cosine theta plus I sine theta, which is r e to the I theta. I can then act with my linear system on f star. I'll get some answer, call it g, right? That is the same as L acting on f plus L acting on this other piece with an I in front of it. So if I want to know what L acting on f is, I just take the real part of g at the end. And why is this powerful? It's powerful because most of the things we do are easier to do to e to the I theta than they are to do to cosine theta. Right? Cosine theta, what's its derivative? Negative sine theta. What's the derivative of e to the I theta? No, what's the derivative of e to the I theta? Derivative of e to the ix is? No, is? Yeah, I e to the ix. Okay? So it's easy. Much easier derivative. Notice, what did we say earlier? So the derivative of cosine theta goes to minus sine theta. The derivative of e to the I theta goes to I times e to the I theta. In both cases, it's a phase shift of pi over 2. We keep track of the actual phase shift, which is the key thing you want to know about. A linear system does two things. It can change the magnitude and it can shift the phase. Linear response or linear systems is about changing the magnitude and shifting the phase. And those are much easier to keep track of with e to the I theta than they are with sines and cosines. And so it is an incredibly powerful mathematical technique that allows us to do a lot of things. And there's really two big examples. There's quantum mechanics, where the wave function truly is complex, and it's not just a mathematical trick, it's actually what you have to deal with is complex numbers. And the other big one is what I just said, linear response in classical systems, one of the most common being electrical circuits. And just real briefly, let's look at a case of a capacitor. And we'll finish with that. Right? A capacitor is given by Q equals CV. There's the relationship, right? The capacitance is the amount of charge you can hold for a given voltage. If I want to relate the voltage to the current in a capacitor, what do I do to this equation? What's the relationship between any of those variables in there and current? Well, V equals IR is for a resistor, so we're getting close. But which of these variables is related to the current? Q. And how is Q related to the current? dq dt. So dq dt, which equals the current, is going to be C dV dt. This is a linear response situation. So now imagine I deal only in oscillating voltages, only an AC circuit, where V naught is e to the I omega t. I'm going to use my complex notation. Notice dV dt is now I omega V naught e to the I omega t, which is I omega V. So if I plug that in to here, I see that I equals I omega C V, or V equals 1 over I omega C times the current. What does that equation look like? From AC circuits. We had V equals IR. This looks like V what? This is the impedance. V equals IZ. The impedance is the linear response function. It's coming from a differential equation and an assumption of an AC voltage using complex notation. That at the end you would take the real or imaginary part depending what you started with. So your complex impedances are only reasonable algebraic equations because you've made a particular assumption about an underlying differential equation. And so the other power of linear response is to turn differential equations into algebraic equations when we are assuming a periodic behavior. And we're going to look at all of these applications in a little more detail, particularly with some of the problems you'll be doing on Thursday.